So our first speaker is Nikola N.Andrejic. He will talk about autonomous particles. This is a paper that was just released on the archive, and so it's very recent. And please go ahead, Nikola.
Okay, thank you, Vitaly. Vitaly forgot to say that it's a paper that was written based on work that we together did in like previous months. And yeah, as of today, it's online on archive.
Yes, indeed.
Okay. Let me start. So the outline of this talk is the following. So first of all, I will briefly mention some of the main problems in autonomous driving that were inspiration for this theoretical work. Then I will talk about inspiration for how we attack some of those problems, and it comes from field theory, as we will see later on. And all of that, like all of the two of these points motivated us to define something that we call autonomous particles. So I will also go through explaining what do we consider, what kind of objects are autonomous particles. And all of that will be presented through a simple numerical example, through a simple toy model that we actually studied, a particular instance of autonomous particles. Okay, so broadly speaking, we can divide problems of autonomous driving into three groups. The first one is obviously environment detection. And as many of you know, today it's done through different types of sensors, like complex systems of sensors that are integrated together, such as many cameras, LiDARs, radars, whatever, GPS data. There are many ways to detect your environment. Then the next group of problems would be decision making, i.e., based on what you have detected, what decisions you should make. And then finally, you need to translate those decisions into real world, i.e., you need to produce a desired real world output, and that is a subject of vehicle control, broadly speaking. We do not talk too much in our work about these, like we consider these two to be solved, although we do briefly talk about vehicle control, and our main focus is on decision making, how to make decisions based on what you have detected in your environment. So obviously a lot of information comes from your environment, like many pictures, many sensor data, whatever, like, but just imagine one image. It contains many pixels. It can contain millions of pixels, and then you can have many images. You can have other sensor data. So the input, as we would say in machine learning, the input has many features. The information is large, but you can make very few decisions, at least compared to the amount of information that you get, right? So there are very few actions that you can actually make based on those, based on the information, which inevitably means that not all of the information is relevant, i.e., probably you can extract and I want to make clear. So this isn't about the standard procedures of important feature extraction and stuff like that. That's usually discussed in standard machine learning. As we will see, this is much more fundamental, like how to actually extract relevant information from what we get from the environment. And we propose a certain way of coarse graining the received information. For this, we find inspiration in nature, i.e., from field theory. One of the first examples of field theory that you would learn in school or wherever is like classical electrodynamics, which means, you know, charged particles and they move and they interact between each other. and so here I write, let's see how electron thinks, how electron makes decisions where to move. So let's say we have an electron here. This is an electron, negatively charged particle, and in its environment it has many other charged particles, and each of them can be positioned anywhere, really, can move with arbitrary velocity, and all of them interact with this electron, and it has some position and velocity at time t. How would its position and velocity be updated at time t plus some small time interval epsilon, a small time-like parameter epsilon? Like in the next time step, how will it move? Well, we know from electrodynamics that its acceleration is determined only by E and B, by the electric field vector and magnetic field vector at its position at time t. And they determine the acceleration through Lorentz force law. So probably many of you have seen the expression for Lorentz force in this form here. And we can interpret this equation in two ways. So the first way would be local interpretation, the so-called local interpretation. The acceleration of this electron, so these particles here that we call sources. So this is a test particle, and these other particles that influence its motion, we call them sources. They emit bosons, which in electrodynamics are photons, right? We know that. And these bosons, they arrive here, and then this electron only sees locally the bosons that arrive there. So it only feels the bosonic field at time t and at position where it currently is. And based on that, it calculates, let's say, or the force that is exerted upon it is determined by the bosonic field. But there can also be another interpretation, which we call the global or non-local interpretation. And there we can say the following. These electrons, they do not emit any kind of physical bosons, but this electron here, it scans its environment. And it can determine the positions and velocities of all of these source particles at any given time, possibly within some precision. But in principle, we can even assume that the precision is arbitrary. And then, based on that, it calculates, like on its own, it calculates what should be E and what should be B, and it calculates the Lorentz force, and then it makes a decision how to move. And so when we look at this global interpretation, we see that that's much like self-driving vehicles. You detect your environment, then you somehow integrate that information, and then you make a decision how to change your current velocity or position or whatever. And because of that, we say that this global and obviously, like these two interpretations, they are equivalent. They produce the same results, at least for electrodynamics, for this particular field theory. But this second point of view is much more powerful for solving problems of autonomous systems, as I already explained, because in certain ways it's much like that. Okay, so now let's apply this model to autonomous particles. So what are the autonomous particles? Well, they are objects that obtain information about each other and about their environment. Like in principle, they are able to do that. However, they cannot communicate with each other. Like they cannot know what decisions other autonomous, like a certain autonomous particle, it cannot know exactly what decisions will other autonomous particle make, but it can detect current information at time t about all of them. Next defining feature of autonomous particles is they have a certain goal. What goal? Well, we don't know. We will see for self-driving, at least for a toy model of self-driving, we can define a certain goal, but they have a goal. They want to do something. Then they have a neural network connected to them. And the goal that they want to achieve is encoded in the learning objective of that neural network, i.e. in minimizing the loss function of the neural network. Okay, so in our case, the goal would be arrive at the destination while avoiding collisions with other autonomous particles. Okay, that is a simple goal that you can formulate for your autonomous particle. Now, how their dynamics is determined? Well, first they scan the environment and obtain as much information as possible. In our case, we would use relative positions and relative velocities with respect to other autonomous particles, and also they know everything about their destination, like where they want to arrive eventually. Then we coarse grain this information and we calculate only a few parameters. That here I use the term Galilean invariants. Later on we will see what exactly are those. Similarly, how Electron would calculate E and B, although E and B are not themselves invariants, that's important to mention, but still E and B are they're coarse-grained information of the dynamical state of charged particles, of like source particles. And then each of our autonomous particles, it moves in the next small time step such that their goal is met, i.e. that the corresponding loss function is minimized. And that we do through learning, through training. We update weights and biases of the neural network connected to them. Now the loss function also must be expressible in terms of these Galilean invariants that we will see later on, as I said, what they exactly are. So the loss function also, so the Galilean invariants are the inputs, and also the loss function needs to be expressed in terms of them. Okay, so this would be a setup of our toy problem. So for example, this is a autonomous particle. This is its destination. It wants to go there, but it also wants to avoid colliding with others. So it needs to make moves, and it needs to make decisions not to change its velocity and position such that it doesn't collide. Now, why Galilean symmetry? Well, first of all, autonomous driving has a preferred frame, and that's ground, a road, earth. Like when a policeman stops you on a highway and tells you you moved at such and such speed, that speed with respect to ground. Like there's obviously, in driving, there is obviously a preferred frame. Then speeds are small compared to the speed of light. For example, if the speeds of the car were comparable to the speed of light, we would have to use Lorentzian symmetry, not Galilean symmetry. Now, what are Galilean invariants? Well, Galilean invariants are numbers. I think I used the term in the previous slide, parameters, but they're numbers that do not change under rotations, translations, and Galilean boosts. In other words, two observers whose frames are related by a fixed rotation, translation, or move with respect to each other with constant velocity, they must measure the same value of a Galilean invariant, like if that's a truly Galilean invariant. Now let's see examples of them. This here is the distance. So this is a particle alpha, this is a particle beta, and these are their position. This is the magnitude of the relative position between them, which is the distance between those two particles. Well, that's a Galilean invariant. Any two observers, however they are rotated or translated with respect to each other, or if they move with constant velocity with respect to each other, they will measure the same distance between the same two particles. Then also relative speed between two particles is a Galilean invariant. And there you can see why you need the requirement of moving with constant velocity with respect to each other. Like if you're stationary or if you're on a train that moves at constant velocity, you will always measure the same relative speed between the two objects, So that's a Galilean invariant. Then also here we give other examples of Galilean invariants. For example, here we see coarse graining. Coarse graining here means summation over, so here we have a particle alpha, and then we sum over all other particles beta. like here we have a distance on some power and then an exponent of that distance as well. So this is a Galilean invariant that contains many terms inside of it, and each term is separately a Galilean invariant. Okay, and here we have another example of that. And we should mention then that in addition to Galilean symmetry, in these two last invariants, you also have permutation symmetry, i.e. Identities of the particles can be exchanged because we sum over beta. Okay, what about other symmetries? Like, can we have other symmetries? As I said, we could use Lorentzian symmetry instead of Galilean symmetry. In our example that I will later show, we also have permutation symmetry in some of the invariants. Okay, now let me talk about the neural architecture. So what's important about the architecture of the neural network connected to each autonomous particle is that it has following units. So first is what we call detection layer, and it should be able to detect relative positions, relative velocities with respect to other particles, and also relative position and relative velocity with respect to its destination. But for simplicity, everywhere we will use that the destination is stationary. So this R, capital R alpha, is the position of the destination, and capital V alpha is the velocity of the destination. And we will use that capital V alpha is 0. Then, using all of this information, we construct a certain number of invariants, and then these invariants are used as inputs of the training module. Training module, its name says that it's trainable. It contains parameters of the neural network, weights and biases, that are changed by learning, that can be updated by gradient descent. And then the training module produces outputs. It produces what particles' velocity should be at the next time step and what particles' positions should be at the next time step. Now the learning is initialized by the loss function. So we impose upon this velocity and position a certain loss function. And as I already said, here we encode symmetries. So, and also, since the loss function must be expressible in terms of these invariants as well, we also encode symmetries. And there is one important difference between symmetries and between invariants here in this layer and the invariants that appear in the loss function. Why? Well, these invariants, they contain data at time t, like at time step t, where you detect your environment. But obviously you want to make decisions how to move and what to do at the next close time step, let's say at some t plus epsilon. So this H alpha contains the same invariants, is expressible in terms of the same invariants present here, but they are evaluated at t plus epsilon. Now, where's the problem? Well, the problem is you don't know where other particles will move at t plus epsilon. So you need to make estimates about their positions and about their velocities. And we make those estimates in a certain way. If you're like, you can make them, you can, for example, reuse the data at time t for other particles. You can say that their positions and velocities will not change by much, but also there are other ways to make these estimates. Okay, in our numerical example, we use following invariants. So this is the velocity of particle alpha. And here I fix epsilon, like the small time-like parameter, to be 1 in some arbitrary units. Or you can read this t plus 1 as velocity at the next time step. So you know the velocity at time step t, you want to get the velocity at time step t plus 1. Okay, so this is the velocity of the particle of t plus 1, this is its position, and this capital R alpha is the position of the destination. And if you look at this term here that appears in the loss function, by minimizing it, what do you get? you get that V alpha is perfectly aligned with the direction that points to towards the destination, right? Because this is the position of the particle minus the position of the destination. So if this is the destination, and if this is the particle, this vector here is actually this vector here, right? And you want your velocity to point like this. So by minimizing this term, when is it minimized? Where exactly where your velocity is anti-parallel to this vector. So by minimizing it, you are actually meeting the goal of moving towards your destination. And these two terms, we call them collision preventing terms. Why? Well, they contain, again, R alpha at t+1. What will your position be at t+1? And this rho beta is what you estimate will be the position of every other particle beta, and we sum over all other particles. But what is the estimate, the position of every other particle beta that you have detected in your environment? And obviously, when you're too close, like when your particle alpha is too close to any other particle beta, this term blows up. So it's minimal when you're far away from all other particles. So this term prevents you from coming too close to other particles. This term here is similar, but it also contains a relative, or at least what you estimate will be a relative velocity between the two particles, and it prevents you from moving head-on towards other particles if you're too close. For example, these two are moving almost head-on, and once they get close, this term will become large, and since your goal is to minimize the loss, then they will change their velocities accordingly, so that this term gets reduced. Now, these degrees here need to be chosen carefully. We discuss this in much more detail in our paper, but these terms, they need to decay fast enough, like with relative distances between particles, such that far away particles, they do not influence decisions made, for example, here, for avoiding this collision here. Okay, so here I extract from our numerical simulation, I extract a few examples of trajectories that we get. So this is an example when an autonomous particle is far away from all other particles. And there, these two terms are really small, and this term dominates. And as we explained, this term makes the velocity of this particle align as perfectly as possible with the direction pointing towards the destination. So when it's far away, it will always go directly towards this destination. But however, if it approaches another particle, it will deform its trajectory such that the collision is avoided, as you can see. And here we have three interesting examples of how the particles actually avoid collision. So here we have an example where both particles choose to take the left turn. Like if you will, we can say that they learn the left-hand traffic rule. Like both of them turn left with respect to their own velocity. Here the situation is a bit more complicated. One of them, this blue one, it turns right, but the red one with red trajectory turns left. But and that happens purely by chance. And then this blue one, somehow it remains persistent in its decision to turn right.
Well, Nikola, it's not by chance. It's just because the other particle learned the other hand rule before.
Okay, yeah, in previous, yeah, you're right.
So it first learned some rule, and then it meets another particle that has this the different rule, and so they have to renegotiate.
It needs to, one of them, no, okay, what happens by chance is that one of them unlearns the previously learned rule. So this one, it starts...
Well, maybe also, no, sorry, Nikola, I interrupt you. Maybe not by chance, but again by the loss, right? So the one that has in a better position to advance.
Yeah, I agree.
it will just take over, and the other will have to give up and
I
say,
agree.
okay, well, I've been traveling in Britain.
I agree on that, but that also happens by chance. I mean, which one of them would have larger loss? But okay,
yeah, by
you
chance
can
meaning
say,
like who comes closer to the point
Yeah,
of their interaction. Yes.
But you
So-
can say that probably here and here, you already know which one would persist and which one will unlearn. So, well, I mean, it starts turning left, and this one starts turning right, and then they start moving in parallel. But there is no way to avoid, like they will move. If they both persist, they will move in this direction, like both of them, right? So one of them has to give up, and as it turns out, this one with the red trajectory, it gives up and then it turns right. And that's
so
how
Nikola,
the
we're also running a
avoided.
little bit out of time, so
Okay.
maybe we can get to the simulations to just see
Okay,
how
okay. And yeah, that's the last thing that I have to show you. So how that happens in the simulation. I hope you can see it. So they move towards the destination until they come close to each other, and then they make decisions to avoid each other and continue moving towards their destination. So that's the general behavior. Also, I'm trying to see if we can. Okay, so these two learn the opposite rule, if you can see. So they move in parallel, and then very late, one of them gives up and slows down and goes behind. Also, these two here. So the resolution of the encounter is much simpler if they learn the same rule at first than if they learn the opposite rule. But since we only have very few neurons, I forgot to mention that each neural network that I use, the training module has 30 neurons in total, so it's very easy to learn and unlearn those rules, left-hand and right-hand rules. Okay, so let me return to this. Well, yeah, let's see the video, and that would be it for today.
All right, so let's open the floor for questions. We still have a few minutes. Don't be shy, and you can just speak up. There was one question in the chat, so maybe Nikola, you can check that answered correctly. The question was about electrodynamics. Why you would use that as opposed to something more complex than that? And I said it was just an example, right?
Yeah. So it's I would say it's probably the most familiar example to everyone. Like when you say physical field, when you like the first field that you learn in elementary school that you mentioned are electric and magnetic fields. So that's why I use that example. But it can really be any other field theory.
All right, there are no further
yes, I have a question.
Go ahead, Vikram.
Was there an example or a situation where a car was not able to reach its destination?
Actually, no, it learns very quickly to reach its destination. Like it always reaches its destination. And yeah, in the simulation, whenever it reaches the destination, we reinitialize it to some other random point. So it continues running like indefinitely until you stop it, and it always reaches the destination. Like it's impossible. Like we didn't witness any example of it, either of collision or not reaching the destination.
Yeah, I mean, you could have modified your destination term, right, so that it doesn't favor.
Yeah. If you choose a bad destination term, like a bad form of the term that makes you go towards your destination, then it might miss it. But with this term, it always worked perfectly.
There's another question in the chat. Let me read it from Sergio. Is this if this is true? Do you think there is a neural network behind physics theories, the physical theories?
Well, that's maybe the ultimate question that we want to answer. Like
very good question, right?
One difference between autonomous particles and actual particles is that actual particles, they do not make their decisions, at least as we look at them today. They do not make their decisions by learning. They are predetermined. Like you know that the electron will move according to Lorentz force law. but maybe it learned it. Like maybe there is a loss function that you can impose upon particles such that in the long run they converge to making decisions as if they follow Lorentz force law. Now we don't know that. Like, can you find a local loss function such that that's true?
Work in progress, right, Nikola?
Yeah. That's work in progress.
Right.
Maybe you can
Other
train your
questions?
electrons.
Sure, exactly. Other questions? All right. Thank you, Nikola.
Okay. Problem.